Hi there, and welcome to this video on A-Level Chemistry for the AQA specification, focusing on the topic of chemical equilibria, Le Chatelier's principle and Kc, and in particular on the equilibrium constant. Hi, I'm Manisha from StudyMind, where we help you to revise A-Level Chemistry with our helpful revision resources tailored to your subject, your specification, and to you. If you're new here, please make sure to click that subscribe button, and whilst you're watching, please leave any comments down below about anything you're unsure of. If it's your first time watching, make sure to let us know so we can send you our free revision resources. We also have helpful timestamps to guide you through the video. So, let's get started. Welcome to lesson 2 of 2 in this tutorial, covering the equilibrium constant for homogeneous systems. This is the second video in our series of 2 lessons on the topic of equilibria, Le Chatelier and Kc. In the last lesson, we looked at reversible reactions at equilibrium and Le Chatelier's principle. Here are the key learning objectives for today's lesson. First, we will look at the equilibrium constant, and then we'll look at how to calculate it. Here are the AQA specification points for this tutorial. Feel free to pause the video now and read through them before we begin. We'll start off by looking at the equilibrium constant. The reversible reaction, shown here, would reach equilibrium after a while, after which the concentrations of the reactants, shown here as A and B, would equal the concentrations of the products, shown here as C and D. These concentrations are called the equilibrium concentrations. The equilibrium constant is defined as the ratio of concentration of products to the concentration of reactants. The equilibrium concentration can be calculated by finding the equilibrium constant. Now, we will look at constructing an expression for Kc. The equilibrium constant Kc can be deduced from the equation for a reversible reaction by using the following expression, shown here. Here, we can see an equation for a reaction. Let's use our equation for equilibrium constant here. We've substituted in the concentrations of the products and reactants as shown. The big letter in the square brackets will show the concentration, whilst the small letter will show the moles in the equation. Our next specification point focuses on concentrations. Here, we can see that there are 2 types of reactions. The first is homogeneous, and the second is heterogeneous. Kc only holds true for homogeneous reactions. These are the reactions where the reactants and the products are in the same phase. They could all be in solution or all be as gases. A heterogeneous reaction is when the 2 are in different phases. Some could be solid and others could be liquids. If you have a heterogeneous mixture, you can still find out Kc. For a reaction involving solids and gases, you can calculate Kc, but ignore the concentration of the solids. Similarly, for a reaction involving solids and liquids, you can calculate the Kc and ignore the solids as well. However, for a reaction involving liquids and gases, you cannot calculate Kc, but you can calculate something called the Kp. Now, we will look at calculating Kc ourselves. By substituting the concentrations into the expression we learnt earlier, we can work out Kc.
we have to work out the units each time as they will vary from calculation to calculation. Here's how to calculate Kc. First of all, we must write an expression for Kc using the reversible reaction equation. Next, we will substitute the molar equilibrium concentrations into the equation to calculate the value of Kc. Finally, we must calculate the units of the value for Kc by substituting the equation without the units without putting the numbers in. Let's attempt this practice question. Pause the video now to try it yourself. Here's the answer. Let's go through it step by step. First, we need to write out our expression for Kc. Here, we can say that Kc is equal to the concentration of hydrochloric acid squared divided by the concentration of H2 multiplied by the concentration of Cl2. Now, we can substitute in the molar equilibrium calculations. So here, we would say that Kc is equal to 0.33 squared divided by 0.67 times 0.83. This gives us an answer of 0.196 to 3SF. Finally, we can calculate the units of the value for Kc by just substituting the equation with the units without the numbers. So here we would have moles per decimeter cubed squared divided by moles per decimeter cubed multiplied by moles per decimeter cubed. These will all cancel, leaving us with no units. Our next objective is to perform calculations involving Kc. Sometimes you will have to calculate the equilibrium concentrations in the reaction before you can calculate the value of Kc. First of all, we would need to calculate the number of moles of reactants at equilibrium. Next, we can calculate the molar concentrations by dividing each number of moles by the total volume of the vessel. Then, we can write out an expression for Kc and substitute the concentrations into the Kc expression to calculate its value. Since Kc units will vary depending on the question, our final step is to work out the units. Let's try this practice question now. Pause the video to attempt this by yourself. Here's the answer. Let's see how we got there. Here, we can see that CO and CH3O are in a 1-to-1 molar ratio. This means that the number of moles of CH3OH produced must be equal to the number of moles of CO reduced. However, H2 and CH3OH are in a 2-to-1 molar ratio, meaning that every time 1 mole of CH3OH is formed, 2 moles of H2 are used up. We can use an ICE chart to summarise the information we did in step 1 to work out the equilibrium number of moles. ICE is simply an abbreviation. I stands for the initial number of moles, C stands for the change in number of moles, and E stands for the equilibrium number of moles. We'll use one of these charts shortly. Let's try another question. For our first step, we need to find out the number of moles of CO and H2 at equilibrium. To do this, we'll draw the ICE chart we described in the last slide. So So here we'll have our moles, we'll have CO, H2, and our product, which is CH3OH. Down this side, we're going to write down ice, which is our initial moles, our change in moles, and our moles at equilibrium. This is how we get ice. First, let's put in our initial moles. These are, for carbon monoxide, it would be 0.18398. Hydrogen is 0.22046. And CH3OH is 0. Now we can calculate our change, which will be minus 0.051716. For H2 it will be minus 0.103432, and for CH3OH it will be plus 0.051716. Now we can calculate our moles at equilibrium. This will be 0.132264, H2 will be 0.117028, and CH3OH will be 0.051716. Now we will calculate the molar concentrations by dividing each number of moles by the total volume of the vessel. So here we'll be dividing by 1.00, as shown here. This means our values will stay the same. Next, we will calculate the Kc. So here we need to write out our expression, which is going to be CH3OH divided by CO multiplied by H2 squared. This will be equal to a value of 28.6 to 3SF. Now, we need to work out the units for this particular answer. In this case, it will be moles per decimetre to the minus 6. Therefore, our final answer for Kc will be 28.6 mole dm to the minus 6. If the value of Kc is known, we can calculate the concentrations of substances in a reaction at equilibrium. First of all, we will write an expression for Kc using the reversible reaction given. Next, we will substitute all the known equilibrium concentrations into the Kc expression. Finally, we will rearrange the equation to find the unknown equilibrium concentrations. Here's a practice question to test the knowledge we've just learnt. Feel free to pause the video now and have a go at this question by yourself. Here's the answer. Let's go through it together. First, we need to write out our expression for Kc using the equation given to us in the question. So here, our expression for Kc will be equal to the concentration of hydrogen multiplied by the concentration of carbon dioxide divided by concentration of carbon monoxide multiplied by the concentration of water. Now we will calculate the molar concentrations by dividing each number of moles by the total volume of the vessel. So we'll substitute in our numbers here. So we'll have 4.5, which was our value for Kc, is equal to the concentration of hydrogen multiplied by the concentration of carbon dioxide divided by 2.5 times 3.0, giving us a value of H2 multiplied by CO2 divided by 7.5. Step 3 is to rearrange to find the unknown equilibrium concentrations. So here we would do H2 multiplied by CO2 is in fact going to be equal to 4.5 times 7.5, leaving us with an answer of 33.75. Therefore, H2 will simply be the square root of 33.75, which equals 5.81 moles per decimetre cubed to 3SF. We know this because the molar ratio of H2 to CO2 is going to be 1:1. Now we will look at the qualitative effects of temperature on Kc. The value of Kc will change if the temperature is changed, as the temperature change will affect the direction of the reaction. An increase in temperature will favour the reaction in the endothermic direction. A decrease in the temperature will favour the exothermic reaction. Here we can see 4 factors affecting Kc. These are changes in product, concentration changes, and catalysts. If the temperature change increases the amount of product formed, the value of the numerator will increase, meaning that the value of Kc will be higher. Now let's look at a decrease in Kc. If the temperature change decreases the amount of product that is formed, the value of the numerator will also decrease, leading to a lower value of Kc. Now let's look at change in concentration. If the concentration of either the reactants or products is changed, Kc will not be changed. Using a catalyst in the reaction does not affect the value of Kc. It will simply mean that an equilibrium is reached faster. We've now covered all the specification points for this tutorial. Feel free to skip back through the video and re-watch anything you are unsure about. We have now completed Lesson 2.
If you liked this video, make sure to catch our latest videos by subscribing down below and leaving a comment on a topic that you'd like to see a video on. Click here to watch more videos on our series of A-Level Chemistry, or visit our website studymind.co.uk for past paper compilations by topic and specification.